Okay. So I'll talk about the field theory of vortices just as one topological matter. In this talk, there is an old part and a new part, paper published this year. So I hope you will have time for this. That's a work done in collaboration with Jeroen van der Brink, the IFW Dresden, Zohan Wisnov there. In my student, the most recent work, I will just flash the results of my student Vera Shita. And let's start first with the first part of the talk about the Witten effect in superconductor topological insulator heterostructures. And it's a well-known fact that the electromagnetic response in 3D topological insulators is described by so-called axion electrodynamics. And for some reason, the PDF is corrupted. Ooh, okay. Let's imagine that the questions are not showing correctly in this PDF. No, it's not a PowerPoint, it's a PDF. A PDF should be a valid format, right? Yeah, the axion electrodynamics of topological insulators, as I was mentioning, contains this additional term, which is a E dot B term, which is induced by quantum effects from the bulk, right? So this theta is the flux of the Berry curvature from the band structure, and alpha here is the fine structure constant. Because this comes from the Bloch space, the flux of Berry curvature in Bloch space, this theta is periodic, it has a theta plus 2 pi invariance. And if you have, in additional, time-reversal symmetry or inversal symmetry that's preserved, then theta is equal to pi. There are some recent experiments by the group of that shows this Kerr and Faraday rotation experiment, where you have they measure this, they measure the rotation depending on this parameter alpha times theta, also by the group of Laurens Bollekamp. Can you go to the next slide, please? So one thing that you know that is happens when you have such a type of term is the so-called Witten effect, an axion-induced charge fractionalization in the presence of magnetic monopoles. And what the Witten effect, can you show a little bit lower the rest of the slides, please? Yes. Yeah, there is this charge here, which is induced. You usually have only the charge, the n times quantizer charge, but there is a correction due to this axion term in the monopoles occur a fractional charge. Of course, in our solid, we don't have monopoles, but we have vortices. Next, please. Next. Next. Thanks. So in the case of the vortices, we have, if you take the Gauss law is modified, it gets modified, this is the usual thing, div of E equals 4 pi rho. And there are two extra terms if theta is no uniform. One is gradient theta dot B, and the other is div B. In the case of the original Witten effect, gradient theta is 0 because the system is infinite in size, but div B is non-zero because you have a monopole. In your case, it's the opposite. The div B is 0 because you don't have a magnetic monopole. In this case, a true magnetic monopole. I'm not talking about effective monopoles that Valerie and Christina are talking. I talk about electromagnetic thing. And in your case, this case is 0, but the gradient of theta changes. Okay. For example, you have that here inside the Ti, theta is non-zero, but then when you cross the interface here to the superconductor, the type 2 superconductor, here this bar is a cartoon of vortices, theta is 0. Then there is a boundary condition at the interface, then when you change you can compute the charge using the Gauss law. Is an exercise that simple electrodynamics exercise. And then you get a correction to the charge, which depends on the magnetic flux of the vortices. A little bit lower to show this, please. Can you? Yeah, thanks. This flux is given by is determined by the number of vortices of quantized cost of vortices in the sample. So then you have this correction. So in principle, this should also arises in this example. Then what you have done back in 2018, you have to consider a generalization of London theory. So exactly found the exact solution, vortex solution for this problem. So these are the London equations. Usually you use only one London equation with this with the superconducting current, which is gradient of phase minus 2e times vector potential. But because of the axion term, you have an extra contribution due to the electric fields that appear here. And then you have also to include the Gauss law, which is here. Epsilon here is the usual, the dielectric constant. So we solve those equations of the usual boundary conditions, not the usual boundary conditions, but the usual boundary conditions for the London theory are modified by those theta term, this axion term. And then instead of having 0 here, the boundary conditions on the derivatives, they are discontinuous because you have interface, and you have this theta term. Now, the solution for the electric potential, it's of course, this is the exact solution, but in terms of an integral, I cannot solve this integral exactly. There is a Bessel function here. There is this smearing function that depends on z, which is depends on the parameter theta and the dielectric constant. But this is alpha theta over pi, or for example, pi, theta equal pi. So this is the order. This becomes a square here. So you can use this f for theta equals 0. And this is the inducer, the electric field inducer by the vortex. Can you go to the next slide, please? And the magnetic vector potential is more or less of the usual type. Just for comparison, since Christina was talking about a monopole, so this is the vector potential of a monopole with a Dirac string going to the south pole. And here is the example that is also relevant for us in some cases for so-called pure vortex. The only difference is that you have magnitude of z. You don't have a hedgehog. There's also known as pancake vortex. We have all lines entering below z equals 0. Entering the vortex, all the lines above z, above 0, going out of the vortex. And here is our situation. Our situation asymptotically for R much larger than the London penetration depth. You have for z smaller or equal to 0 singular in 1 over R. And looks like a monopole for z greater than 0. This looks exactly like a monopole in this case. Here are the plots of the exact solutions, actually. So because just plot the integral, here you'll see the magnetic field. But because of the interface, you have also radial component of magnetic field. So here is z equals 0, that you are here. And here are the electric fields. So the radial component of the electric fields. Here you can see this sunrise here is the z component of the electric field. Go to the next. Sorry that I'm going too fast, but because I want to keep it more or less in time, because maybe we'll still have another speaker. This is the charge density that is induced at the interface. Can you show the formula as well? Yeah, this inducer charge is given by NE times theta over pi, exactly the inducer charge at the interface, which is a fractional charge. If theta equals pi, this is a fractional charge, N equals 1 for one vortex quantum. This is E over 4. Okay? Now, there is a consequence. Maybe I should skip this slide because we were not in time, but there is a consequence. This is a slide of Shapiro steps, but if someone is interested, I can come back to it. I want to show you some other thing. The angular momentum. Yes, the angular momentum is non-zero for this vortex because remember from your favorite textbook in classical electrodynamics, the angular momentum of the electromagnetic field, there is the orbital, the mechanical part plus the field angular momentum, which is E cross B, which is the momentum. Then you make R cross E cross B. This is the angular momentum. And it turns out that this can be calculated also exactly from the London theory. You will get the result that the total angular momentum is quantizing in funny ways, minus n squared. N is a vortex quantum, h bar theta over 8 pi. For theta equals pi, this is 1 over 8. Now, we proposed in our paper an experiment to measure this. It is a Josephson junction array. You measure the differential conductors, but to create here a vortex island that where you should see a periodicity in the differential conductors of 4 pi because of this charge quantization E over 4 for the case of theta equals pi. It turns out someone did this experiment exactly like you said. Next slide, please. Recently, it's published this year in Nanotechnology by the group of Alexander Brinkman. He made this Josephson junction array of this island, but unfortunately, he didn't see the effect we predicted. There are maybe a number of reasons for that. One thing is that the critical current is too large for the charges are too large to see this fractional charge quantization. Now I will just flash now quickly. Let's go to the next topic with two components. There's three more slides. So if the next speaker that he can do this, this is the work done by my student, which has some overlap. If you look at the equations, the physics is different, but there is overlap to what Christina was saying. So to take the two-component topological superconductors with some, which actually was, in your case, original motivation was not a topological, not a superconductor, but quantum antiferromagnets with an easy plane anisotropy in the CP1 representation. Then you have, besides this Maxwell term, you added a Chern-Simons term. All motivation was to find out whether with the Chern-Simons term you have a secondary phase transition or not, because without the Chern-Simons term, the numerics shows that the phase transition is first order. This kappa here, the coefficient, is n over 2 pi, where n is called the Chern-Simons level. Here, what I just said, it is equivalent to topological quantum antiferromagnet with easy plane anisotropy in the CP1 representation. It turns out that this theory has an interesting London theory that's a little bit reminiscent to what we saw in Christina's talk. There are two types of London theory that you have to consider because you have two-component antiferromagnet. One is first without the Chern-Simons term, you can get by duality this London theory that features, instead of one London vector field, H, it features two gauge fields, B1 and B2, coupled to vortex lines. These N's are vortex fields. There are two of them. You'll notice here is interesting. Usually in the London theory, we'll have just one B. We expect B2 equals 0. But here you have B1 plus B2 squared, not only B1 squared. This means that this London theory has gauge invariance. If you do a gradient of theta, shift this by gradient of some theta, it is 1 by minus gradient of theta, this gauge invariance is preserved. Now, the second London theory that's possible if you take E squared to infinite limit, which was one of the limits Christina also considered in her talk, where the Maxwell term of the original theory is absent. And then what you have an interesting theory with which a Chern-Simons term, which contains two gauge fields. So you couple, it's the same structure that's topologically massive. This is usual mass, and here is a Chern-Simons term with B1 and B2. And what is interesting about this theory is that it can be exactly bosonized. Right? So that's first. There are two things here. For next slide, please. First, you can make a bosonization duality in 2+1 dimensions for these examples for the level 1 Chern-Simons. This consists of a theory again featuring two gauge fields, two massless Dirac fermions coupled to this. This is QED, two-component QED. And what is also interesting is that indeed this features a quantum criticality with quantized critical exponents. Here is a critical exponent for the correlation length. that you computed. This exponent is not for the order parameter because it's gauge dependent. This is exponent either for the correlation function of a composite field for the magnetization. Actually, we did this. I can remember that we did this originally for quantum antiferromagnets. This feature of very large critical exponents, which is typical of so-called something that I don't have time to tell you. That's what I just said that I just flashing this is so-called deconfined quantum critical points. So then I conclude this talk. But the first part is that of the talk is look at the exact vortex solution of TI superconductor structure. The vortex induces electric field, a fractional electric charge. You have a non-zero angular momentum. I didn't have time to talk about the Shapiro steps, but there is some additional things related to Shapiro steps. The second conclusion for the second part is that you have you consider the topological two-component superconductors have quantizer critical exponents forming a distinct universal class. You establish also explicit bosonization for massless direct fermions in 2+1 dimensions. With this, I thank you very much for your attention. Sorry for the technical problems, and thank you very much. So this is here you have this is breaking time reversal, and your question is probably whether the dual model breaks time reversal or not.
Yeah.
Yes. Well, it actually breaks. Can you go to the next slide, please? Yes. Thanks. Yeah, there. You can introduce new variables here. Let's say you call B1. Actually, because of these two gauge fields, only one of there is one gapped, topologically gapped mode. The other is gapless because you can write, for example, B plus, which is B1 plus B2, and B minus, which is B1 minus B2. So then this B plus term will break time reversal. There is one Chern-Simons term for B plus.
Okay.
Does this answer the question?
Yeah.
Yeah, okay.
You mentioned there is, in London relation, there are two vector potentials or two fields in the topological version of London theory. Can you make some comment how you can interpret this experimentally and so on?
Yes. Thank you for the question. So the question, if you have two order parameters, right, you have also possibilities of two vortices, two types of vortices. In this case, there are vortex loops, but doesn't matter. So imagine to have two types of abricos of vortices. And associated to this two types of vortices, now you hear me again. Sorry. You have technical problems with the mic sometimes. So you have those two types of vortices. The experimental, the physical interpretation of B1 and B2 is this the fields associated to these two types of vortices associated to the phases, winding phases of the two order parameters.
Did you also consider Josephson vortices that you can have in Josephson junction? In the system?
No, I don't. Actually, this is an interesting question because this system, this is also mentioned in the paper. Sorry that I didn't have the time to show details on that, but one application of this problem, the theory here, let me show you, here, this theory is a theory for a typical theory, this type of Chern-Simons term is a typical Chern-Simons term for quantum Hall bilayers. There are experiments already made a long time ago, in 2000, where they see a Joson's effect across two quantum Hall, integer quantum Hall bilayers. But they didn't consider that case, as far as I can tell, the case of Josephson vortices. This would be an interesting thing to do that in the terms of this correspondence to quantum Hall bilayers. But the two component superconductors, actual superconductors, you have to see there are several superconductors with two component order parameters, like iron-based superconductors, the other stuff, right? D-wave superconductors, now there is one thing that is quite a new thing. Actually, you were interested on that as well, where you twist two D-wave superconductors. There is this is very recent, actually. If you twist at 45 degrees, you have two D-wave superconductors, the order parameters becomes D plus ID prime, which is, in this case, you can also consider two order parameters from superconductor 1, superconductor 2. This has, the vortices have also topological property in that case, if you look at the nodes, if you linearize around the nodes of this new order parameter, you can solve the, this actually was done recently by myself, friends, you can solve this, the Bogoliubov-de equation and get Majorana zero modes in that case. And I believe a similar type of theory can be applied also in that case. In this case, we will have also a possibility of having other types of vortices there. Thank you.
More questions?
Just one question. Sorry, Flavio.
Yes?
So your superconducting model is an anion, you have anion superconductivity, is that correct?
What superconductivity is that?
Anion.
Anion. Yes, looks pretty much like anion superconductivity for the second part of the talk, you mean?
Yeah,
Yes.
I'm talking about the second.
Yes.
It's an anion superconductivity, and anion superconductivity at the beginning was taught for ITC superconductor. Do you think your model can describe this to anion superconductor?
Yeah, well, in theory, yes, but experimentally, it's very hard because, yeah, it's very hard experimentally. Unless.
But it's a model of anion superconductor.
Yes, it is. But you can, what we discuss in the paper, experimentally, you discuss in the paper, no, it's only one paragraph, a short paragraph in the paper, is not about measuring fractional statistics, but about quantum Hall bilayers. But it will be interesting to see if it does apply to anion superconductivity. Again, in this case, you might consider these new materials, these new structures, which are when you twist the D-wave superconductors. There might be something because the Majorana states are bound states with the vortices, and they have, if the vortices move, these Majoranas are actually anions, right? They are anions. So then I think you can do something in that case experimentally, but unfortunately, in my case, you are right, it's anion superconductivity, but in abstract sense. Okay, it's not a true. I don't have any ideas for direct experiment on that at the moment. For quantum computation, well, in this work here, I didn't consider explicitly the Majorana fermions. Usually, Majorana fermions are used for topological quantum computation. Technically speaking, we didn't do that, but there is potential for that. I have another paper, but a completely different topic. Which has a relevance for quantum computation, but this must have relevance for quantum computation, but I don't know, I would not know like a spontaneous how to tell you this. In one sentence it would be difficult. The only thing I can say is that if you consider the Majorana bound states to the vortices, that will be a path towards it, but it's a kind of deja vu answer, right? But it's the answer I have at the moment.